All right, good morning. Okay, as a reminder, all of the Chapter 6 homework has been due already. The Chapter 6 test is due. Y'all should have received an email from me. I actually gave y'all an extra, 2 days on the homework and 1 day on the test. Because of just the occasional my math lab issues still persisting with one or two people, I didn't want to be unfair to everyone, so I gave everyone an extension. So you had tons of time for this test. The results were pretty good overall. I want to say my average was low mid 70, which is exactly where I expected to be for this course. So we're doing pretty good, all things considered. The Chapter 7 homework is available. I believe I've had that available for a little bit, but I just wanted to make sure that you know. And please don't wait till the last minute to do it. I had a lot less homework completion this go around than previously, which it was the fewest number of sections. I mean, it was only 2 chapters of the material so far, but it was less homework sections to complete and you had more time to do it. So if you didn't have a great homework completion for the second test, please make sure that you get things back in gear for this one. So Chapter 7 homework is available. Please complete it as we're moving along. And we are going to finish 7.1 right now with the area of an oblique triangle. The area of an oblique triangle. So remember, oblique means there are no right angles. So there's no 90-degree angle. So it's either all acute angles or two acute and one obtuse being larger than 90, acute being less than 90. And we showed you kind of a diagram last time as to what this revolves around. But our area, let me maximize this, is equal to 1/2 B times C times the sine of A, capital A, or it's going to be 1/2 times little a and C times the sine of angle B, or it's going to be 1/2 times, which haven't we done, A and B, right? Yes, A and B, and then sine of big C. Now this is for the triangle. Again, I tend to make these look equilateral, but that's not necessarily my intention. So if we have our angle A here, our angle B here, our angle C here, that makes the sides little c here, little a here, and little b here. And these aren't necessarily drawn the same way as I had been doing for the law of sines, but that's irrelevant. It never matters where you decide to put your A's, B's, and C's. Now, there's 3 of these formulas because it really doesn't matter what you call the letters. This is really just one formula, but relative to what corner you're calling yourself in. And I call this a corner of information. So let's just look at the first one. Let's say we needed to use the first one. That means we've got side lengths B and C and angle A. Well, here's side length B, here's side length C, and here's angle A. So this right here would be our corner of info. This right here is what I call a corner of info, because you can just draw a corner with the info you had, and then everything else is the unknowns. This angle's unknown, this angle's unknown, this side's unknown. And this is what we see when we need to use the law of cosines in the next section. And that's why I went on a small little rant that this should, in my opinion, be in the next section, even though it uses a sine. So where does this come from? If you just did, let's say, go back to black. Remember in the past, the area was 1/2 the base times the height. Now, when I say B here, I'm saying base, not just a random side B. So this side I have to call little b, and then this dotted length would be the height, and we'd say it's just half a triangle. Okay, Let's see. B. I'm trying to decide when I want to call some things. Let's call this A and this angle C. All right, that's the version I want to use. So if this side length is A, this angle is C, I'm calling this B, and I'm using B two ways for the base. That means this is little c. And then the other angles I'm not going to draw because they'll be unnecessary. So H here, on the left side, we have got a little right triangle. And H could be found by using one of our trig functions. We need to know H, that's the unknown. We're assuming we have A and we have angle C. Well, side A would be the hypotenuse of that left-hand triangle, that left-hand right triangle. I didn't want to be confusing. And then H would be the opposite. So you'd want to use sine. The sine of angle C would be H over A. If you multiply both sides by A, the A's cancel. And we get that A times the sine of C, angle C, is equal to H. So we're just going to plug that in. To where we see H here. So now our area, instead of being 1/2 base times height, it's 1/2 the base times A sine of C, and then we just rearrange it to make it look a little prettier. So that is the proof of one of those three. I just proved the right one, and the other two proofs are exactly the same. You just change how you letter everything. Instead of calling this B, you could call this B and this A and this C. We only have to prove it once because, again, it all means the same thing. It's just about perspective. So you are supposed to remember these formulas, or what do I always say? You can verify. So you can remember the old school one and then do this proof really quickly, because this shouldn't take you long in theory after you've tried it 2 or 3 times. Because if you're going to remember something based on a concept, based on a proof, you should practice that several times before you're going to just need to have it stuck in your head for a test. Again, I don't care if you're remembering the old formula and the proof to get the new formula, or if you just memorize at least one of these versions. Because as long as you remember, okay, these sides have to be different than the angle. These sides are different than the angle. These sides are different than the angle. Everything should be fine. So let's try out an example with this. And we're up to example 3. Again, we're continuing 7.1. I said it earlier, but I didn't write it. Find the area for problem A. And I'm going to do a drawing, kind of a mediocre drawing. Let's try that again. A little better. And I'm going to say this angle is 73 degrees. This length up here is 7, and this length over here is 8. And we want to find the area of this. And this is a corner of information, exactly what I said you have to do, or you need for this formula. So again, you can call these whatever letters you want to. If you call this 7 the A, and you call this 8 the B, that means the 73 degrees has to be angle C. Or, I'll go back to that version in a minute. If you call this B and this C, then this has to be angle A. And then there's a third version, but I'm not going to write all 3. I'm going to stick with what I had originally, A, B, C. Remember, if you don't like using capital letters, then that would be gamma instead. Ooh, that was weird. Those are the same thing. So the area is equal to 1/2 times A, which is 7, little a, times B, which is 8, times the sine of the angle between them, 73 degrees. And then we just put those in a calculator, which I need to pull up. If your screen went blank for a second, it'll be back in a second. Go. Ram cleared. So let's make sure our mode is correct, make sure we're in degrees, which we are not. Tends to happen when I reset this digital calculator. So I can quit. So we got to do 1/2, same thing as 0.5, but I'll write 1 divided by 2, times 7 times 8, and then times the sine of 73 degrees. Drum roll, close our parentheses, drum roll, and we get 26.7765, blah, blah, blah. I typically round to 1 decimal. Remember, make sure to pay attention to what my math lab tells you to do. I don't want you to lose credit because you round incorrectly in this class. That would be just silly. So 26.8 is what we're going to round to. So that's approximately 26.8. Now, I didn't give this thing any units. If I had said this was 7 inches and 8 inches, this would be in inches squared. Remember, the area is always in inches squared or meters squared or feet squared or miles squared. B. And this time, instead of giving you a picture, I'll give you the just the info directly. Let's say little a is 40, and let's give units, meters. Let's say little c is 121 meters, and then angle B is 11 degrees. Now again, we can tell this is a corner of information because the angle we have is between the two sides. If it wasn't, then it would be either angle A or angle C. And if you don't trust this, you can always draw it up. Now, I don't have to do this drawing. I can draw it however I like. I'll go back to drawing it this way. Ignore the little extra bits I drew there. And I can call anything I want. Let's make the A up this top right one. Make that 40. Let's say the C is the bottom one. So this will be our 121, and these are meters. And then the 11 degrees we'll say is, it has to be this one. If this is side A, that has to be angle A. If the bottom is side C, the top has to be angle C, meaning this is angle B, and then this would be side B. Now I'm not gonna find any of these 3 unknowns. All we want is the area, which again, we have a corner of information, so we can use our formula that A is 1/2 times the product of the sides that surround the angle. So 1/2 times the 40 times the 121 times the sine of the angle between them, which is 11 degrees. And then we just put that in our calculator. Oops, share calculator. So 1/2 times 40 and 121 times the sine of 11 degrees. Close our parentheses for good practice. And we get 461.757, how appropriate, but 757 is going to round up to 0.8 when we round to the nearest tenth. So 461.8. But I did give you units, something I don't do a lot in our examples. But that's not just meters, area is in meters squared. And that should be a squiggly equally sign technically. There we go. So that is the area of an oblique triangle. Hold on, give me 1 second. I got something going on. All right, sorry about that. So that will close out 7.1. So let's move on to 7.2. which I have already mentioned several times. 7.1 was the law of sines. 7.1 was everything using a sine in it, whether or not I think the area of an oblique triangle should be in this section because it's the same application style, just a different trig function. The law of cosines is specifically used for SAS and SSS. Now remember, S's mean sides and A's mean angles. So that's side, angle, side, and side, side, side. So we use the law of sines when we have two angles. That was the first set of examples we did. Those are the easiest. There was always one answer. If you have two angles, you can always find the third by doing 180 minus the other two. Then you can always find the other two sides by using the law of sines. Then we got into the side-side angle case. And that was when the angle given is not between the sides. See, the way they write SAS is implying that this angle is between the sides. So that's what, sorry, draw. When you do it like that, that means the angle is between the sides, the given sides. All angles are between sides, of course. I mean by the given numbers. So side-side angle meant the angle was not between the given sides. That meant we had a completed pair of information, which meant we could always use the law of sines. When you're given SAS, you do not have a completed pair of information. When you're given SSS, all sides, you do not have a completed pair of information. So the law of sines is out. So we have these new formulas that we're going to have to use. And I can type all these up. And there's three versions of these, just like there were three versions of the area of an oblique triangle. And it's kind of interesting that this rule of three keeps popping up. So the area of an oblique triangle had three versions of it. The law of sines had three sides, which means there are technically three different versions of the law of sines, because it could be the first equal to the second, the first equal to the third, or the second equal to the third. So keeping with this theme, there are three versions of the law of cosines, and that's because what you call A, B, and C can completely be transposed by someone else, and yet all the information is still intact and accurate. All right, so our three versions. We have little a squared. Oh, I'm not going to be able to type this up. I lied. I keep forgetting this does not have a way to make exponents. I don't want to say I keep forgetting. I've only had to look for it once before. So a squared is equal to b squared plus c squared, and these are all little letters, minus 2bc times the cosine of angle A. A squared equals b squared plus c squared. This kind of looks like Pythagorean right here, but rearranged. Then a minus 2 times b and c. So all the sides on this side are the ones that are given. The a, in general, would be your unknown. It doesn't have to be. But if you were given the angle between them, if this was SAS, you would want the b and the c to be the given sides and the angle A to be the given angle. The second version of this is b squared is equal to a squared plus c squared minus 2ac times the cosine of angle B. And the third version of this is c squared equals, and if you're good with patterns, you might be able to go ahead and figure this out on your own. So let's see, when it was a squared, we used b squared and c squared here, we used b and c here, and then the angle A here. When it was b squared, these are the other side lengths, and then the angle B. So c squared should be the same pattern of squares and pluses and minuses, but with the other letters A and B. So it should be a squared plus b squared minus 2ab times the cosine of angle C. You have to memorize these. You are supposed to have these memorized. Again, take-home tests are a thing now. But you are supposed to be memorizing these under a traditional classroom, which means when you go into calculus, maybe these would come up and your calculus teacher might not be giving them to you on a formula sheet somewhere. What calculus teachers give you and don't give you is going to vary wildly. I typically tell you to memorize the things that a calculus teacher would not give you. And again, you might say, oh, I'm having to memorize 3 things. No, you're not. You're memorizing one thing only. And that is that the side squared, whichever side you want to call it, is the sum of the squares of the other 2 sides minus 2 times the product of those same 2 sides and then the cosine of the angle between them. That's the way I always memorized it. I never memorized all 3. I only memorized 1. If you need to memorize all 3, that is up to you. And again, I just want to make sure I'm writing this down, that SAS, side angle side, is what I call a corner of info. Side angle is not. How do I want to draw this? Let's go this way. I'm trying to mix up how I draw my triangles. So if I call this side A and this side B, that means this is angle C. I'm going to draw it on the outside. This is a capital C, not a lowercase c. Just to make sure. So that's what I call a corner of information. Side angle is not. Okay, so let's try this out. And this is going to be fun to type in on a digital TI-83 for me, but that's okay. Example 1, let me switch back to black. And we're going to complete the triangle. For A, problem A, I'm going to draw it like this. And again, my triangles are not necessarily drawn to scale. Please do not take them that way. Let's call this a 10. Let's call this a 12. And this a 32 degrees. Hold on, give me 1 second again. Sorry, I've got something going on today, so I might have to do this 1 or 2 more times. Just give me about 30 seconds. The joys of working from home, am I right? Okay, I'm back. So here's problem A, and the numbers for this triangle, the way I've drawn this, we've got a corner of information because the 2 sides and then the angle connecting the 2 sides with notes. I didn't have to give it to you this way. I could have given it as A equals B equals C equals, or one of those would have to be an angle. So if you want to label all the other things, if I call this 10, let's call this A. Let's call the 12 B, and then let's call this side over here C. So if the 10 is the A, that means angle A is down here. The 12 is the B, that means angle B is up here. And if the C is over here, that means 32 degrees is angle C. Again, I could have called the 10 little b and the 12 little c, and that just would have made this over here little a, and all the angles would be reappropriated. And then there's a third version I could have called this. It does not matter. So we're going to use calling the letters this. I'll put the formula up here 1 more time. C squared equals, that's an equals. A squared plus B squared, it's the sum of the squares of the other sides, minus 2, then the product of the other sides. Kind of looks like a factoring formula. It pretty much is, minus this extra little cosine bit. Then the cosine of the angle between them, which was the 32 degrees. Why did I write 32 degrees there? We're supposed to be just using the formula. So cosine of angle C. Pardon me for that. Then we'll go and plug the numbers in. So we get C squared equals little a squared plus little b squared. That's the 10 squared plus the 12 squared. Minus 2 times the 10 times the 12 times the cosine of the angle between them. And that's where I'm going to write the 32 degrees. Now, you can simplify this by hand in a couple of steps first if you want to. You can say, oh, 10 squared is 100, 12 squared is 144, 10 times 12 is 120, times 2 is 240, but then you can't add that to the 100 and the 144 because of the cosine. At that point, you'd have to say you're, what's that, 244 minus blah, blah, blah. Then you can type in your calculator. But why not just go ahead and type in the calculator as it is? And I'm going to go ahead and round to 1 decimal place, which, by the way, calculators are allowed. I believe I've said that before, but calculators are always allowed, even if this was an in-class test from here on out. Because, yeah, you can get an analytic answer for this one, but you're going to get extremely ugly analytic answers for the rest, and nobody wants to have to deal with that. So you really always want to be punching these in a calculator. All right, new share, calculator, turn it on. All right, so that was 10 squared plus 12 squared. I think I have these in the opposite order, it doesn't matter. Minus 2 times 10 times 12 times the cosine of 32 degrees. Let me double check my mode. We're still in degrees. Close the parentheses. So 10 squared plus the 12 squared, or 12 squared plus 10 squared, minus 2 times 10 times 12, or 12 times 10, because the order of products doesn't matter, times the cosine of 32. Drum roll, and we're going to round this to the nearest tenth. So 40.468 is going to round up to 40.5. I did not give units, so that's just 40.5. But this is c squared. To find c, we take the square root of both sides. So we get the square root of c squared is approximately the square root of 40.5. And you could have also just done this analytically and taken the square root up here. That would have also been acceptable. So c is approximately and I can actually do this. If I type square root of answer, I hit second and then the negative symbol to do that. That's just going to take the square root before I rounded. I want to compare these two things just so you can see that there could be error propagation. So taking the square root of the actual thing gives us 6.36. Let's see what the square root of 40.5 is. Let's see if it makes a difference for this problem. 6.36. Now, since I'm only rounding to 1 decimal place, this is actually accurate to 2. So it doesn't seem to matter if we had rounded and then taken the square root first. Now, if I said to round to the nearest tens of thousands of places, then yes, it would matter because 6, 3, 1, 3, they start being a little different. But for us, we're just going to get 6.4. 3 6 rounds up to 4. So C is approximately 6.4. All right, so there's one of our pieces of information. So when do we use the law of cosines? When we have a corner of information. Now we've got C, which is this opposite side, now to the angle we were given, which means we now have a completed pair. When you have a completed pair, that means you can use the law of sines. I almost said cosines there, the law of sines. Now, if I had 2 angles at this point, we'd go ahead and find the third, but we still don't have a second angle, which is what we're probably about to do. So we've got side A, side B, and side C. We only have angle C, so C is the completed one, so that'll be the left hand for our law of sines. So remember, the law of sines goes the length over the sine of the angle equals length over side of angle equals the length over sine of angle. So for the law of sines, the length we said was 6.4 over the sine of its angle. That's the sine of 32 degrees. So that's the completed pair. I could put it on the right-hand side if I wanted to, it doesn't matter. And then let's attack these in alphabetical order. So I'll go after what I call the A first. So that's the one that has the 10 in it. So we're gonna go, actually, I wanna mix things up. I'm gonna do the B. I decided to mix things up for this problem. So we're gonna go after the B's. So 12 over sine of angle B. which we do not know. Again, it does not matter which one I did. I'm just mixing things up. Last class, I always went in alphabetical order, so I'm changing that because it doesn't matter. Cross multiply, and we'll get 6.4 times the sine of angle B equals 12 times the sine of 32 degrees. Now we're supposed to be solving for B because that's inside a sine. We're going to have to eventually take an inverse sine, but first we got to get rid of the 6.4 in front of it. And this is not going to divide nicely. As I said last class, it doesn't always divide nicely. Sometimes it does, sometimes it doesn't. These little arrows are just saying continue on. So that tells us sine of B. Let me give myself a little more room. Is equal to 12 times the sine of 32 degrees all over 6.4. And then we take our inverse sine of both sides. Now, some people will just go straight to B equals inverse sine. Some will show the work. I like to show the work most of the time. Whatever we do to one side, we're doing the other. Inverse sine and sines will cancel each other out. Sorry, which tells us that B is equal to the inverse sine of 12 sine of 32 degrees all over 6.4. Okay, so that's what we're going to have to type in our calculator. Where'd it go? Inverse sine, so second sine. 12 times the sine of 32 degrees. Make sure you close your parentheses. Then divide that by the 6.4. Close the parentheses again. Drum roll, rounded to the nearest tenth. That would be 83.5. 83.5. So angle B, oops, is approximately 83.5 degrees. Now, we could definitely do the law of sines again to find angle C. I'm sorry, angle A, angle A. We have C already. That was given. We could use the law of sines to find angle A. We could go 6.4 over sine of 32 degrees equals 10 over sine of angle A, and do the same algebra and trig again, but that would be a lot longer. Once we know two angles, which we have the 32, we have the 83.5, we can find the third angle by doing 180 minus those. So angle A is 180 degrees minus 32 degrees minus 83.5 degrees. It's 148 minus 83.5 is 64.5. So that is angle A. So that is how we use the law of cosines for a side angle side case. Okay, let's try another one. B. And I'll give you a picture again. I really like giving pictures for these. And remember, my picture's not necessarily drawn to scale, as I hope you can tell since I'm calling that 10 degrees. And this 24, and I'm gonna call this bottom side 31. So I am gonna decide to call the 24B this time. Oops. So I'm gonna call the 24B. I'm gonna call the 31C. And then that means that A has to be this side, which makes 10 degrees angle A. Angle B has to be opposite the 24. Angle C has to be opposite the 31. Now, again, my convention of labeling these A's, B's, and C's is irrelevant. There's 3 completely different versions of this that would all be accurate. But what you have to make sure is that a side is opposite of its angle. I can't have this be side B and this over here be angle A or C. That's not possible. So again, that's how I decided to name things. We have, once again, a corner of information. Here's our corner with 2 sides and an angle. So we're using law of cosines. Now, since I call this A, that's the unknown. The version that we'll use is A squared equals B squared plus C squared minus 2BC times the cosine of angle A. So plugging those in tells us that A squared is equal to 24 squared plus 31 squared minus 2 times 24 times 31 times the cosine of 10 degrees. That's a degrees, not a square. And again, you could go ahead and take the square root of both sides and do this completely analytically without rounding, but we saw that the rounding the rounding propagation wasn't really severe to the nearest tenth. So let's do this in 2 steps. So we will take the square root after the fact. Calculator. So we're going to do 24 squared, turn it on first, 24 squared plus 31 squared minus 2 times 24 times 31 times the cosine of the angle between them, which was 10 degrees. Which rounded to the nearest tenth is going to give us 71.6. And then we're going to end up taking a square root of that. I'll write that out in the next on the whiteboard, but we will end up taking a square root of this, as you'll see. So let's take the square root of 71.6. And we end up with 8.5 rounded to the nearest tenth. And make sure you know how to type these in your calculator. So the A squared version, that was the 71.6. Then we take our square root of both sides. And when we took that square root, we got 8.5. So A is approximately 8.5, rounded to the nearest tenth. Now that we have a completed pair, we have angle A and side A, we can use the law of sines to find the next side. So the completed pair are the A's, so we'll go A over sine A. So A is 8.5 over the sine of 10 degrees. Now, what I was mentioning before, that you can do this without a calculator, is just ugly. Instead of having 8.5, what you would have written there is the square root of this whole thing, but you'd want to at least simplify the 24 squared, the 31 squared in this product. And I wouldn't do that on a non-calculator test. Those numbers are a little big and annoying. But I wouldn't do it to begin with, so it's irrelevant. Let's go after the B next. Let's go back to alphabetical order. So 24, that's side B over sine of angle B. We're going to cross multiply, which will give us 8.5 times the sine of angle B equals 24 times the sine of 10 degrees. We got to isolate the B, the angle, but that's inside of a sine. So eventually we'll have to take an inverse sine, but not yet. We got to get rid of the 8.5 first by division. And if you remember, I'll even admit, if you don't, last class, I forgot to do that division, but I caught myself because I realized, oh, I can't take the inverse sine with an 8.5 there. All right, so that'll give us inverse sine, leave a little room. Sorry, not inverse yet. I'm thinking ahead. Sine of B equals 24. Leave room. sine of 10 degrees over the 8.5, because that's not reducible. And then we take our inverse sine of both sides. Which tells us that angle B, when we round it to the nearest tenth, so this is what we're going to have to put in our calculator. Inverse sine of 24 sine of 10 degrees divided by 8.5. So inverse sine, second sine. 24 times the sine of 10 degrees, close that parentheses, then divided by the 8.5, and close that parentheses. Drum roll and round it to the nearest tenth. We get 29.36, so 29.4 degrees. That's going to be 29.4 degrees. Now, I want to do something to make sure that nobody makes this mistake. We have a reciprocal button next to sine, and that's a -1. And we said when we didn't introduce the inverse sine, watch out, Rambo. Sorry, that's my dog. He's messing with me right now. Where was I? I got distracted. Okay. We had said that we want to make sure we don't confuse this notation with inverse. So what someone might do is hit sine and then the reciprocal button and think that this is going to work. Let's see what happens if we did this. 24, then the sine of 10, close that parentheses, divided by the 8.5. Let's see what happens. Error syntax. And that's telling you that you done goofed, you made a mistake typing things. And if you hit go to, it might even show you the error. And yep, it's saying, hey, you can't have a sine and then an inverse of something. That's just weird. All right. So back to what we had originally. I'm recalling my functions, second enter. That was the real deal, and that was the 29.4. So angle B is about 29.4 degrees, rounded to the nearest tenth. Now that we have two angles, 10 degrees and 29.4 degrees, we can find the third, which we're deciding to call angle C, is 180 minus the others. That's 170, 140.6. Yes, 140.6. That's angle C. Questions? All right. So that's example 1A and B. Let's do C next. Let's do another one. How are we on time? Good, 30 minutes. And this time I'm going to give you letters instead of drawing the picture. Little a equals 19. Little c equals 4. And then big B equals 61 degrees. So I did not give you a completed pair. Remember, a completed pair means I gave you all the A's, all the B's, or all the C's. This is a corner of info because this is the angle between sides A and C. So we're again going to use, no surprise, law of cosines. So we're going to use the law of cosines, and since we have little a and little c, that means we need to use the version that has little b squared equal to. And that would be a squared plus b squared plus c squared, excuse me. Pythagorean habits, am I right? Minus 2 times a times c times the cosine of the angle between them, which has to be b. Plugging those numbers in tells us that b squared is equal to 19 squared plus 4 squared minus 2 times 19 times 4 times the cosine of 61 degrees. Rounding this to the nearest tenth, after we put it in a calculator. Let's see, we got 19 squared plus 4 squared, I think. Yes, plus 4 squared minus 2 times 19 times 4 times the cosine. And I don't have to hit times. If you haven't caught on to that, you can, or you can skip it. And that was the cosine of what? 61 degrees. Close our parentheses. And that turns out to be 303 point blah, 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 rounded to nearest tenth. That would be 303.3. So 303.3 is the squared version. Remember, this was equal to b squared. So I'm going to take the square root of that again. So the square root of 303.3 is going to give us 17.4 rounded to the nearest tenth. I'll show all that work on the whiteboard. So this was about 303.3. So then we take the square root of both sides. We don't have to do a plus or minus because this is geometry. This is trig. There's no negative side links. So B turned out to be about, oh, what was that number? 17.4. Okay. Now we can use law of sines because we have a pair completed. We have the B's completed. So with the B's completed, that's 17.4 over the sine of angle B, which is 61 degrees. And I'm going to go after the C this time. So I'm going to go after the C. So equals 4 over sine of angle C. So let's cross multiply this. And we'll get 17.4 times the sine of C equals 4 times the sine of 61 degrees. We got to isolate that C, which means ultimately we'll have to do an inverse sine, but not yet. We got to divide by that 17.4 first. So I'm going to leave a little space. That'll give us sine of C equals 2, little space, 4 sine of 61 degrees over 17.4. Then we take our inverse sine of both sides. Again, some people don't show this step. Just like some people don't show adding 5 to both sides. Some people don't show dividing by 17.4 on both sides. It's up to you how much work you're showing. But that tells us C, and we're going to be rounding to the nearest tenth, so I'll do as approximately that in, well, not yet. Just have it analytically written. That's inverse sine of 4 sine of 61 degrees over 17.4. Then I'll go as approximately. And we're going to type that in our calculator. So inverse sine. What were my numbers again? 4 times the sine of 61 degrees. Close that parentheses. And then that was divided by 17.4. Close that parentheses. We're going to round this to the nearest tenth. Drum roll. That gives us 11.6. And this is an angle, so 11.6 degrees. So C is about 11.6 degrees. Okie dokie. Now we can find the other angle, the third angle. We have angle B, we have angle C. Let me make sure that looks like a capital. So angle A should be 180 minus the other two. So minus 61 minus 11.6 degrees. Let me write that a little neater. And that was an answer, by the way. And when you do that subtraction, It's 119, 107.4 degrees. That's angle A. Let me move this. So I'm leaving a little space here, and I want to try something. Instead of, so when I said you do the law of sines, I went after the C next. I went after angle C here. So this was going after the C's. At this point here, instead of using the law of sines with the 4 over sine of C, let's try something different, okay? So I'm going to try instead for that law of sine step, let's go 17.4 over the sine of 61 degrees. Let's see if we had done this, excuse me, the B's instead, I mean the A's instead, because the B's are completed. So let's go 19 over the sine of A. I just want to see what happens, just to see, is everything going to be square or not? So we cross multiply, which will give us 17.4 sine of A equals 19 sine of 61 degrees. Then we do our division. I'll show that in blue, divide by the 17.4. Well, that seems coincidental. So that they cancel there. So that'll give us, let me go up here. Sine of A equals, leave some space, 19 sine of 61 degrees over 17.4. Let's take our inverse sine of both sides. And that'll tell us that A is supposed to be the inverse sine of 19 times the sine of 61 degrees all over 17.4. So let's type that in our calculator. 19 sine of 61 over 17.4. 19 sine of 61. Inverse sine. 19 sine 61. 61 divided by, that was the 17.4. And we get, wait, what? 72.8. 72.8. So A is approximately 72.8 degrees. Wait a minute. This does not agree with this. So what I'm suggesting here is that the order you attack things can actually matter. When it matters is if there is an oblique angle, but you cannot always tell if there is going to be an oblique angle. This is a problem. Now, if there is an oblique angle, it will always be opposite of the largest side. Now, we don't necessarily know that A is the largest side here initially, but when we found B, we noticed that 17.4, 19 is larger. So because A is the largest side, angle A is going to be the largest angle. Now, if that's oblique, oblique meaning bigger than 90 degrees, remember, inverse sine is not defined outside of 90 degrees. Inverse sine is only defined in quadrants 1 and 4. So all of this process, you can't actually do. You cannot attack one of these with the largest side, because if it's going to have an oblique angle, it's going to fail. This is wrong because inverse sine cannot get you an answer in quadrant 2, only 1 and 4. But this angle is 107.4. I guarantee that that's the correct one. So this is because A is largest angle A may be oblique. Oblique meaning bigger than 90 degrees. Hold on. Let me just continue this down here. And you can't get an oblique angle with inverse sine because it's only defined in quadrants 1 and 4. It's from negative 90 to positive 90. And those are supposed to be brackets, not a parentheses. So if your angle is larger than 90 degrees, which in reality it is, that means you can't use this. So this is a little thing that you have to be careful with. You don't want to use the law of sines to find the largest angle. That is what's important. You do not want to find, or sorry, you do not want to use the law of sines to find the largest angle. So that is the summary I'm going to do here. Oops, get wider, get wider. Let me just start over. There we go. So you do not want to use the law of sines to find the largest angle, because you will not necessarily know the largest angle is oblique. Now, if the angle they give you is already oblique, then you know you're fine. There's no tiptoeing around. So let's go back a couple examples. Here we go. So in this one, I did the B for a reason, because 24 was smaller than 31. 31 is going to be the largest side, which means angle C is the largest angle. And look at this, angle C was oblique. So if I had used the law of sines to go after angle C, it would have been wrong. If you go back to this one, we got the 10, the 12, and the C was the 6.4. Same thing. All right. So this is kind of an important segue into the next type of examples, which is the side case. Text, we're good. All right. So the side case. Always find the angle opposite the largest side first. This is because cosine inverse, or inverse cosine, can find oblique angles. Inverse cosine is defined in quadrants 1 and 2. It goes from 0 to 180. So inverse cosine is all encompassing. That's actually the miracle worker will always get it right. But the formula is a lot wackier. It's a lot more complicated. So we don't want to have to use that over and over and over. It's a pain, trust me. We only want to have to use that once. So we're going to always find the angle opposite the largest side first. That will make sure you go ahead and get the biggest angle taken care of. So if it's oblique, you don't have to worry about it with the law of sines. If it isn't, you still don't have to worry about it with the law of sines. It won't matter which other angle you go after next, but we still, I mean, if you want to try and get the next one down, you can, but it won't matter either way. So the next thing you'll do is then use the law of sines. To get the second angle, and then supplement, which is 180 minus the others, to get the third. In the last section, we talked about the angle case and how there was infinitely many solutions due to the laws of similar triangles. Basically, if you imagine one triangle in your head, double the size of it, that's still true. All the angles would be the exact same. Triple the size, all the angles are still the same. So it's infinitely many answers. That's not how side, side, side works. If you are given the three sides, the angles are definitely all defined. So again, the biggest issue to take a hold of is you do not want to end up doing the law of sines using the largest, or to find the largest angle. You can use the largest angle, that's fine, but you don't want to be finding the largest angle with this because it could be wrong. All right, so let's do another example. Example 2. And we're going to complete the triangle. And I'll draw it up. Remember, I don't have to draw it up. I can give you the sides as A's and B's and C's, alphas, betas, gammas, or I can give you the picture. And let's call this 9, let's call this 12, and this 11. I have not designated these with letters, but I will. Let's call angle A the bottom left one. Let's call angle B the bottom right one, and angle C the top, which makes the 11 the little c, that makes the 12 the little a, and the 9 the little b. Again, my designation of which one's A, B, and C is completely irrelevant. All the numbers would end up being the same in the end, just called different letters. This is side, 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 because I gave you three sides. I did not give you any angles. Whenever you're given side, 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 it's the law of cosines first. It does not, it doesn't arguably matter which one you go after first, except for the fact that you should probably go after the largest angle first. The reason you want to go after the largest angle is to ensure that when you get to the law of sines next, you don't accidentally use that to find the largest angle, because it could be oblique and then it could be wrong. Lots of coulds in this scenario. So A is the largest side. So I want to use the version of the formula that had angle A in it. So that was A squared equals B squared plus C squared minus 2BC times the cosine of angle A. And then we're going to put the numbers in here, but all the numbers are not going on the right-hand side. We don't know angle A. That's going to be capital A. The left-hand side, this little a, we actually know at this time. So this is 12 squared equals 9 squared plus 11 squared minus 2 times 9 times 11 times the cosine of the angle between them. And again, here we're trying to solve for angle A. There's a little more work this time. Last time we just jammed all these numbers in a calculator, but there's a variable here. We got to move everything else away from that. Well, let's do the squaring. That's 144 equals 81 plus 121 minus 2 times 9 is 18. 18 times 11, that's 180, 198 times the cosine of angle A. The 81 and the 121, we're going to add to 202, right? Right. 202 minus 198 cosine of A. Do not subtract those. You cannot do that. You're going to have to subtract 202 on both sides. Black. 144 minus 202, that's negative 58, equals negative 198 times the cosine of angle A. We're still trying to solve for A. We got a number in front of it, so we're going to divide. It's negative, so make sure you divide by the negative. So the negatives will cancel on all the sides. Let me just move up here because I'm going to run out of room. The 58 over 198, yeah, it reduces. I'm not going to worry about that. because it's going in a calculator anyways, equals the cosine of angle A. Then we're going to do our inverse cosine of both sides. So that the cosine inverse and cosine cancel. So that tells us that cosine inverse of 58 over 198. Again, yes, I know that reduces. It doesn't matter since it's going in a calculator, is equal to A, which we're going to round that to the nearest tenth. We didn't do an inverse sign this time because our function here was a cosine, so we had to inverse cosine. Calculator. So what was that? The inverse cosine, second cosine, 58 over 198, I believe. 58 divided by 198. Close the parentheses. Rounded to the nearest tenth. 72.96 rounds up to 73 degrees. Rounding to the nearest tenth ends up giving us a whole. That's fine. 73 degrees is our approximate angle. 73 degrees. There we go. So our largest angle in this triangle is going to be 73 degrees. Now that's not oblique, which means this problem you could have done in an, I'm doing air quotes here because it's not really incorrect, but air quote incorrect order. Again, you were supposed to attack the largest angle by using law of cosines because you don't want to be finding the largest angle in a law of sines because it will be wrong if it was oblique. This problem, angle A, the largest angle, was not oblique. All that means is there's no way that you could have messed this up by doing things in the wrong order. But you don't know that to begin with. You're never going to know that, so you have to make sure you're accounting for that. Now that we have angle A, we have a completed pair of information, the A's, so we can use the law of sines, and let's go over here. So the completed pair is the A, so that'll be 12 over the sine of 73 degrees equals, and because we have the largest one, it doesn't matter whether we go after the B's or the C's next. I'll go after the B's, the 9, just to, I'd say, prove a point. Over sine of B, cross multiply, you'll get 12 sine of B equals 9 sine of 73 degrees. We're going to have to divide by the 12. The algebra that you do for this stuff, as long as you're actually doing your homework, you end up doing very similar algebra over and over. So hopefully you'll get used to it. So that will give us sine of B, leave some space, equals 9/12. Yeah, that reduces to 3/4. I'm not going to reduce it because it's going in a calculator. Leave some space. 9 sine of 73 degrees over 12. If it made a whole number, I'd reduce it. Then we take the inverse sine of both sides. And that tells us that B is equal to the inverse sine of 9 sine of 73 degrees over 12, which rounded to the nearest tenth. Calculator. Inverse sine of 9 times the sine of 73, close it, divided by 12, close it, gives us 45.8 rounded to the nearest tenth. So angle B is approximately 45.8 degrees. And then last, we can find angle C by doing 180 degrees minus A, which is 73, minus B, which is 45.8. It's 107 minus 45.8, 261, 61.2 degrees. So that's angle C. All right. So again, you have to go after the largest angle in the law of cosines because the law of sines will sometimes be incorrect if you're going after the largest angle because it could be oblique. Could. Maybe it is, maybe it isn't. Are my test questions going to be oblique or not? I don't know. You won't know. So you need to approach this in the appropriate order. Otherwise, you're going to get wrong answers, I don't know, about half the time, maybe a little more, maybe a little bit less. I can't say that half the problems have an oblique angle and half don't, but that's about where I'd peg it. So we have not completed this section. We do not have enough time to do another example. As you can see, these are definitely longer problems. So we'll do one more of these next time. And then we'll get into the next section. So please remember that the Chapter 7 homework is available. Please do not fall behind on that. Go ahead and start working on this stuff because there's little subtleties. There's formulas to memorize, and then there's subtleties as well that you have to be careful with. Besides that, have a good day. We'll see you next time on the internet. I'll have this uploaded to YouTube by noon today, right after my next class that I'm going into. Yeah, that'll be it. Take it easy.